Year 12, this is our fourth lesson for the topic of vectors and applications of vectors, and it's for the International Baccalaureate course, Analysis and Approaches. So last lesson we started looking at the products of vectors, and in this lesson we're going to continue, but we're going to look at the vector product, also known as the cross product. Now recall when we worked out the dot product, we ended up with a scalar at the end, which is why it's sometimes called the scalar product. The cross product, which is also known as the vector product, it's the multiplication of two vectors with the result being a vector. And it's going to involve a combination of unlike components. So just like before when we were looking at the dot product, it's important to ask, what is it? What is the cross product? And the cross product, V cross W or V times W, it's a vector that's perpendicular to both V and W. And we'll look at this a little bit later, but it's either going to stick directly out of the page like this or into the page. Now I'm going to work through the proof of the cross product. Let's consider the vectors X, which has components X, Y, and Z, V, which has components V1, V2, and V3, and W, which has components W1, W2, W3. And let's suppose that vector X is perpendicular to both V and W. So that means that the dot products must be equal to 0. So we have X V1 plus Y V2 plus Z V3 is equal to 0. And xw1 plus yw2 plus zw3 is equal to 0. Now what we're going to do is multiply that top one by w1 and the bottom one by v1. And we end up with these two equations. And you can see that we have a common term here. So I'm going to take this equation here and subtract this one. And we end up with this equation. Taking this over the other side, and dividing by this, I have y is equal to z multiplied by v3w1 minus v1w3 all over v1w2 take away v2w1. Now I'm going to simplify this a little bit. I'm going to let t equal z over v1w2 take away v2w1 so that I can write y is equal to this expression here multiplied by t. And if I rearrange this and make z the subject, I have z is equal to this expression multiplied by t. So I've got y and z. All I need now is x. And we're going to substitute back into the very first equation, and tidying up and cancelling, I end up with x is equal to v2w3 take away v3w2 multiplied by t. And putting that all together, we have a formula for the cross product. Now it's quite complicated. It is given in your formula booklet, and it looks like that. Now I'm going to show you an example of how to work that out using that formula, but this is actually not the way that I do these sorts of questions. But bear with me. Find the cross product of the vectors A and B. So there's our formula. We know that this is going to be A1, A2, A3, and here we have B1, B2, B3. So it's a matter of just substituting into the formula, and we end up with negative 6i minus 14j plus 2k. So let's have a look at what I consider to be an easier way to work out the cross product. We're going to use what's called the determinant of a matrix. So if you have a basic understanding of matrices, which you do because you did them in year 11, you can easily find the cross product by calculating the determinant of the 3 by 3 matrix as shown. Now I've had to make this matrix, but it's pretty easy. Across the top I have got the unit vectors, and then I have, this is vector A here, or my first vector, and here's vector B. Now, before we keep going, I need to tell you how to calculate a determinant of a 2 by 2 matrix. So it'll look like this. Instead of having these square brackets, we actually use absolute value signs, and we've got 4 parts to this matrix. And to work out the determinant, I'm going to go A times D, take away B times C. Okay, it's that simple. So A times D, so cross from the top left, A times D, take away B times C. Okay, so now that you know how to work out the determinant of a 2 by 2 matrix, I'm going to show you how to work out the determinant of a 3 by 3 matrix. It's going to involve 3 parts, the part involving vector I, the part involving vector j, and the part involving vector k. And I'm going to work through it really slowly so that you understand. But once you've practiced this, you'll actually find that you will be able to work out the cross product in one line without a formula, which is pretty cool. All right, let's start with the part involving I. I'm going to cross out the row and the column that involve I. And what's left is a 2 by 2 matrix, which I'm going to write down. I'm going to write down these absolute value signs to show it's the determinant, and I'm going to multiply that by I. Then I'm going to subtract and do the same thing with j. So I've wiped out the row and the column involving j, and I'm left with a 2 by 2 matrix that I'm going to work out the determinant of, and then I'm going to multiply that by j. And then I'm going to add k. So wiping out the row and the column involving k, I'm left with a 2 by 2 matrix that I'm going to calculate the determinant of here. All right, really important here. So it starts with a determinant multiplied by I minus, super important there, that's the biggest mistake people make, a determinant multiplied by j plus a determinant multiplied by k. All right, let's work out these determinants. We've got minus 4 take away 2, and then we've got 12 take away negative 2, and then 3 take away 1. And calculating that, we end up with the same answer, because it's the same question we just did, negative 6i, take away 14j, plus 2k. Let's do another example. Find the cross product of the vectors a and b. I'm always going to start by setting up the 3 by 3 matrix. It has the unit vectors on the first row, then vector a, vector b. Our cross product has 3 parts, the part involving I, the part involving j, and the part involving k. So let's start with I. Let's wipe this out, and we can see our 2 by 2 matrix here. I want the determinant of that matrix multiplied by I minus, wipe j out. I can see the 2 by 2 matrix there. It's 1, 5, negative 2, negative 1. I want the determinant of it multiplied by j plus, wipe out k, and I can see this matrix here, 1, 2, negative 2, 1. I need the determinant multiplied by k. All right, now let's work out the determinants. We've got minus 2 take away 5, that's negative 7i, minus, and I've got negative 1 take away negative 10, well that's 9, so it's going to be minus 9j, plus 1 take away negative 4 is positive 5, so it's going to be plus 5k. And there's our answer. Now, of course, we have properties of the cross product. Unlike the dot product, order is important. A cross B is equal to negative B cross A. We also have that A cross A is equal to 0. And just like with the dot product, we can expand brackets and we can use FOIL. So why is A cross B equal to negative B cross A? Well, it's to do with the direction of the resulting vector. So remember that A cross B is going to be a vector that is perpendicular to both of these vectors here. So it's either going to stick out of the page or into the page. And one way to tell which way it points is to use what's called the right-hand rule. So you take your right hand and you lie it along the first vector, which in this case is A. And then you curl your fingers towards the second vector, like this. And whichever way your thumb points is the direction of the resulting vector, which in this case is out of the page. If we look at B cross A, then we start with our right hand lying along the B vector, and as we curl our fingers towards the A vector, we're going to end up with our thumb pointing into the page. And so our resulting vector looks like this, and it's opposite in direction to A cross B, which is why we have A cross B is equal to negative B cross A. Now we can calculate the magnitude of the cross product vector by using either the formula square root of each of those components squared and added together, or we can use this formula. The magnitude of V times W is equal to the magnitude of V, magnitude of W, sine theta. Okay, let's look at the proof. I'm going to start by squaring the right-hand side. So we've got magnitude of V all squared, magnitude of W all squared, sine squared theta. Let's change sine squared theta into 1 minus cos squared theta and expand. Now here you can see that we have the dot product all squared. Now let's substitute in the individual components. So V1, V2, V3, W1, W2, W3. We end up with this. Now I'm going to skip a bit here. You can work through it if you want to. But if we expand and then cancel and then factorize, we end up with this. And that is the cross product squared. Now both the left-hand side and the right-hand side there are positive. So if we take the square root, the positive square root of both sides, we end up with magnitude of V times W is equal to the magnitude of V, magnitude of W, sine theta. Here's an example. Consider the vectors A and B. Find the magnitude of the cross product. So we're going to work a bit quicker this time, but we'll always start by setting up the matrix. So the top row we've got IJK, then we have got 1, negative 2, 1, and then we've got 3, 0, negative 4. All right, here is our cross product in one go. Let's see how we got this. I'm going to start with I and just wipe this out here. I've got 8, take away 0, which is 8. Now, biggest mistake people make is we need a minus now for the second term, so there's a minus in here. We're wiping out the column involving J. We've got negative 4, take away 3, which is negative 7, but we have a minus there, so it becomes plus 7. And then finally K, wipe this one out. We've got 0, take away negative 6, which is positive 6, and there it is. 8i plus 7j plus 6k. Now we want the magnitude. That's easy, isn't it? It's the square root of 8 squared plus 7 squared plus 6 squared, which is the square root of 149. Part B, find the value of sine theta. So we know that the magnitude of the cross product is the square root of 149, so we're just going to use this formula. Substitute square root of 149 in here and calculate the magnitude of A and B. We end up with sine theta is equal to the square root of 149 divided by 5 root 6. I showed you this diagram right at the beginning of the video when we were looking at what does the cross product look like. I'm going to return to this now and write a geometric definition for the cross product. So if U is a unit vector and it's in the direction of V times W, then we can write V times W is equal to magnitude of V, magnitude of W, sine theta multiplied by the vector U. Let's have a look at why that is. Here we have the magnitude of V times W. We've just learnt that. But that's not going to give us a vector, okay, because that's a magnitude, it's just a scalar. So we need to multiply it by a vector to give it direction. We need U to be a unit vector, otherwise it would change the length or the magnitude of that vector. So that's why we do it. So here we've got the magnitude of the cross product, and then we multiply it by U, which is a unit vector in the direction of the cross product. Now for the rest of this video we're going to look at some measurement applications, and we'll start with area of a triangle. Consider the triangle formed from the two vectors A and B. If we want to work out the area of this triangle, I'm going to use the formula area is equal to half AB sine C. But in this case it's going to be a half times the magnitude of A, magnitude of B, sine theta. Now that is the magnitude of the cross product. So the area of the triangle is equal to 1/2 multiplied by the magnitude of A cross B. And we can extend this to the area of a parallelogram, because a parallelogram is formed from two identical triangles, and each of them has area 1/2 multiplied by the magnitude of the cross product. So together, the area of the parallelogram is the magnitude of the cross product, which is kind of nice. And lastly, let's look at some volumes. The volume of a parallelepiped, which has 3 vectors as adjacent edges, is given by the absolute value of A dot B cross C. Now let's have a look at why that is. The cross product, B cross C, is the area of that base shape, that parallelogram. And then we're going to do the dot product with this vector here. Now we could use a different definition, because we know that A dot B cross C is going to be equal to magnitude of A, magnitude of B cross C cos theta. And in this case, theta is the angle in between vector A and this upright vector here, because it's going to be the angle between A and B cross C, and B cross C is going to stick upwards out of the page. You can take that one step further and work out the volume of a prism. Now in this case, theta is going to be equal to 0, because it's the angle in between vector A and the cross product B cross C, which is also going to stick straight up. And cos 0 is 1. So the volume of a prism is given by the magnitude of A multiplied by the magnitude of B cross C. Okay, that's it for products and operations with vectors. We're going to move into looking more in depth at 3D space, and we're going to start with lines in space.